So thank you, Professor Schlacher, for this nice introduction, and I will thank the organizer of this very nice conference in Vienna for their kind invitation. It's a great honor for me to give this lecture on what I am interested now in quantum feedback. So as you know, in 2012, Serge Haroche, who is a physicist in Paris, and David Wineland, an American physicist at NIST in Boulder, they share, in fact, the Nobel Prize in physics for measurement and control of individual quantum systems. So this Nobel Prize acknowledges what is called among quantum physicists and also, I will say, engineer, what is called the second quantum revolution. The first quantum revolution was, in fact, to understand and to, in fact, develop transistor and laser, which is a huge collection of quantum particles, okay, going together. So it is quantum statistics. But now we are at a level where, in fact, experimentalists can measure and control individual quantum systems. And so this opened the way, in fact, to what is called quantum technology. I will speak of quantum, in fact, computation, to use as a resource of computation the specificity of a quantum system, which has no counterpart in the classical world, which is coherence and entanglement. So here you have a slide of Walter Reis, which is at IBM Research in Zurich, where in fact he proposed, so he sketched some technology to develop a quantum computer. So you have here superconducting circuits, which are electrical circuits, but functioning at a quantum level. Here you have quantum dots. Here you have typically cold atom, Bose-Einstein condensate, and so on. Here you have photonic circuit also. And here you have something where, in fact, you have, in particular, Blatt at Innsbruck. They have developed, in fact, also support with trap ions in Paul traps. But for all this technology, they are investigated also by companies like IBM. You see here, you have also Google, you have also Intel. So you need, as Walter Reis noticed, scalar modular architecture, of course, because you want to have you want to play Lego with this. So it's important to do that. And you see that control software is everywhere in this thing. Okay. So, but what is the main roadblock in this development? It is the fact that, in fact, quantum superposition and entanglement, it is something which is very fragile. So if you connect your system, which is always connected to the environment, it loses quite rapidly this superposition and this entanglement. So to do that, and in particular in the quantum information community, they develop a certain sort of analog, okay, of error correction, but at the quantum scale. Okay? And this was an idea, in fact, of Peter Shor. So it was in 1995, okay? And this, when you look at what is going on quantum error correction is a simple feedback loop. And it is the simplest feedback loop that you can imagine. It is a static output feedback. Okay? But it is in discrete time. And you neglect in this the bandwidth of a sensor, okay, and also the bandwidth of the actuator. So, but it is still okay with this kind of things. So typically with, in fact, such things, you can, in fact, typical error when you store quantum information, what is called in a qubit, you manipulate it with, I will say, which is called quantum gate, but it is elementary manipulation. The error rate is less than 1%, okay, for typical things. But it is not enough, because not only you want to preserve the quantum information stored in qubit, but also you want to make the operation okay, in a robust way, in a sense, what is called fault tolerance. And in this case, the error rate should be quite below these things. It is not 10 power minus 3, minus 2, but 10 power minus 3 or 4, which is what is called, in fact, the threshold. And in this case, if you use typically such kind of qubit, or a little bit more better, and if you use typically what is called quantum error correction techniques, known surface code, the first estimation that has been done by Martinez and his collaborator in this is that to, quantum error correction, you use redundancy. So not only to define what is called a logical qubit, it will be supported by physical qubit. And in this case, they estimate the number of physical qubit to store just one logical qubit, which is protected from error and which is controllable. It is 1,000, which is a huge overhead. So one of the key issues is that, in fact, but this kind of things has never been built, okay? It has never been built. It's just estimation with what you can do with quantum error correction and the technology of, it was with superconducting circuits. And one of the key issues is to reduce, if you take a qubit whose lifetime is reduced, okay, whose error rate is reduced by several orders of magnitude, of course, the overhead will be reduced because you will need very low order error correction code. So, and I think since error correction is typically in these things, is assumed in discrete time, neglecting sensor and actuator, you can gain precision, but you are at the level where we need to gain precision. Okay? I think that control engineering can play a crucial role to build a logical qubit by just using more elaborate feedback scheme, taking account these small neglected dynamics, okay, and to increase precision and stability. So I hope that I will convince you that our community can bring some important progress to elaborate, in fact, a good, some reasonable logical qubit, and after that to increase, to build a quantum computer. Okay, so here is the outline of my talk. Why I think this? Because first, we have good models. We're very well structured, so we can do something. So I will explain. Mainly, the part of my talk will be on this modeling part, in fact, which is because here you have to understand the rule of the game, but in the quantum world. So it changed with respect to classical world, and especially when we want to play Lego. Okay, then I will discuss, but quite rapidly, different feedback schemes that have been investigated already, but most of them have been investigated by physicists, in fact, either theoretical physicists or experimentalists. Few of them are connected to our community, so I will speak a little bit of that. And then I will conclude by saying, so this kind of things, so models, dynamics model, feedback issue, how can they be used for error correcting, and what is called also, which is an idea coming from two of my former students, Maziar Miraimi and Zaki Lektas, what is called cat qubit, Schrödinger cat qubit. Okay, why it is interesting? Because this kind of support of logical qubit is quite well adapted to continuous model and feedback scheme. Okay. So, first point, modeling here. So, before entering into modeling, I will need to explain a little bit the notation, because one, in fact, of the obstacle to enter into the quantum world, it is the notation. So, you are in an Hilbert space, H. In the Hilbert space, usually, the quantum state is a unitary vector. And the Schrödinger equation, you have your control U. It is just to take your unitary vector and make a rotation of your unitary vector. So it's a rotation of the unitary vector, but in a very big space, of course, but it is just a rotation. So typically, what is called the Hamiltonian. The Hamiltonian is an operator on H, which is Hermitian. So its Hermitian conjugate is itself. It decomposes in general like this. And what is important is that, which has a physical meaning, it's not the unitary vector, but it is the direction of this unitary vector. It's the line. So if you want to remove what is called the global phase, you need, in fact, to write down the equation with, so this is the vector, this is the covector, bra and ket. So it is an operator. And this operator is just the orthogonal projection on the line defined by the wave function. And in this case, you can replace the Schrödinger equation, what is called the Liouville equation, where here you have exactly the same equation, but here you have the commutator between the Hilbert space, the Hamiltonian H, and the density operator. So just, I will always manipulate this. No more in fact, the wave function in the model. We need the density operator. So first, but something which is, it is an ordinary differential equation, a deterministic system with a certain structure, but that's no more. Last point is that the quantum state is a probability law. It is not a position, it is not a velocity. It is a probability law. But the probability law, it is coded into this density operator, which is, of course, Hermitian. Its trace is 1. And it is non-negative. Here it is of rank 1 in this case. But in general, it is the general case. So it is a non-commutative probability law. This changes the rule of the game with respect to classical probability. So the first point here. The second point, which has absolutely no counterpart in the classical world, is the collapse of a wave packet, which means that you assume, it is an axiom, you say, so you assume that your measurement is connected to an operator O, an observable. This is an Hermitian operator. So an Hermitian operator, you take its spectral decomposition, and its spectral decomposition is labeled by your output, what you measure. So you have the eigenvalue, you have a projector of the eigenspace, and for each different measure outcome you get, Y, you have different eigenspace and different eigenvalue. And the eigenspace here, it is a projector, it could be degenerate. It could be of huge dimension. Okay? And you assume that the measurement process is instantaneous. Okay? And when it is instantaneous, you have to take into account what is called the measurement back action, which is when you measure your system, you change your system. And the way it's going on is just this. You have your unitary vector, you detect Y, it gives you a linear plane, you project orthogonally, okay, take the orthogonal projection of your unitary vector on this plane. Of course, its length is less than 1, and you're normalized. Okay, so it's just a projection, this, plus normalization. And the last point is that you get, in a certain sense, in the statistic of this jump, some information on what is the quantum state just by looking at the normalization here, which means that this quantity, which is, in fact, the square length of a projected vector, which is also expressed like this with the density operator, it is just the probability to detect Y knowing the state, the quantum state just before the detection. Okay? And see, this is exactly, so you can do that for the wave function, you can do that exactly with this thing for, in fact, the density operator. And the last point is when you play Lego. You have different quantum system, and you want to define what is, in fact, the global system. And in this case, we change completely is the fact that instead of, in a classical system, you take the Cartesian product, which means the dimension adds. Here, you take the tensor product, which means that the dimension multiplies. We change completely the rule of the game. Okay. And typically, when you want to do this on your composite system, so you will see my system is S, it will be my controller, I will say, or something else, okay? And in general, the Hamiltonian here, it is made of, this is the Hamiltonian of the system itself, that you consider first. And since it doesn't act on the second one, you tensor with identity. This gives you, in a certain sense, a lift. So you have an operator on HS. You want to define the operator on H. Just tensorize with respect to identity on C. Okay, and you get this canonical lift. Okay, so you have this lift. You have exactly the same thing for the controller. And here, all the things is in the interaction. And we know that when you do control, interaction between the controller and the system is important. And you have here, you have the notion of feedback. And the last point, which is connected to the measurement, is that in general, you never measure directly your system. You measure a system who has interacted in your system, which means that your operator here, which is your measurement operator, you don't touch the system, which is the identity here, but it is just a measurement of your measurement system. And because you have some entanglement between your system C that you measure and the system itself, you get information. But it is indirect. So this is the three basic quantum rule that are very well explained in the book of Serge and Jean-Michel Raymond here. So the two very good physicists in the laboratory called Kastler-Brossel in Paris. And this is well explained in this thing, in particular in chapter 4. Okay. So I spent some time on this, and then I will go a little bit more rapidly for the next slide, but it is important. So in all my slides, the bold variable are operator. Okay? Now I can go to stochastic master equation. So if you take an experiment, we are in a classical world. Okay, and the fact that we use the wave function is a sort of intellectual construction. So what we have, so the experimentalist, he has some manipulated variables, as we say in process control, but it is the control input. This is classical signal here. He measures something, at the end of a measurement, you have a classical signal. So you are in the classical world. And in between, of course, you have, in your input-output system, you have correlation between what you are doing in the input to the output you have. And to represent this input-output relationship, what you have when you use the quantum rules that I explained before, in the continuous time and so on, you have here the quantum state, of course, ρ, which will be in this formulation, which is the diffusive formulation. You have a very nice book of Barcelli and Gregoratti, much more mathematics, but on what is called diffusion system. Okay? And in this case, you have a stochastic equation. Here I take only one measurement, where in fact you have the structure here, but you see the key point. So it is as if you say, well, okay, it is something which is close to a Kalman representation with noise. But look, the noise in the system, in the state space, is exactly the same noise as the noise in the output map. This completely changed and this is because of a measurement back action. The measurement back action imposes in the noise that you use to represent the fact that the measurement of a system is a stochastic process is the same in the state and in the output map, in this case. And in between, what you recognize is that here you have a deterministic part. So here you recognize, of course, the Schrödinger evolution. And here you recognize two terms. One term corresponds to decoherence, dissipation. You can imagine that it is as if you have some friction, some irreversive phenomena, D, and irreversive phenomena comes also from measurement, M. And here you see that the dW, which is the same as this one, it enters here with this formula. So you see, you have to be very careful about the order because it is operator. Here you have a trace thing, so something when you are familiar with the Riccati equation, okay? For a Kalman filter, it's something which is something a little bit similar to that. It is on matrix. okay, instead of a vector. Okay. And this kind of stochastic master equation are quite, in fact, useful with electrical circuit but a quantum regime. So I present here the simplest, it is very simplified, by the simplest qubit, which is called Transmont qubit, which is used, for example, at IBM, or a lot of experimental groups in the world use this kind of qubit. It is just, so as electrical engineer, you see you have a capacitor, and here you have a nonlinear inductance. So here you see the energy, you could recognize the energy of a capacitor, and here it is just the Josephson energy of the inductance. And if you take the second order terms just of a cosine, you recognize here phi square around 2L. Just develop cosine up to order 2. Okay, this is a nonlinear circuit, and the way you manage the input-output relationship is just you connect it, your circuit, but with a very small capacity. So the capacity here is much larger than this one, okay, to a transmission line. And you inject waves in your system, and you see what are the scattered waves, and you measure them. It's the way you get this equation, okay? So I will not enter into the detail. The last point, which is important from an engineering point of view, is that this system, you operate around the ground and the first excited state, which gives you a frequency. And since you have a very weak coupling here, your drive is always a coherent drive, which is it has this frequency. And you only control the amplitude and the phase. So your control is not something which is highly oscillatory in the microwave range. So it is something which moves slowly. It's the amplitude and phase things, and why it's exactly the same thing. You measure the amplitude and the phase of a scattered wave after some amplification process. So this is the key Transmont qubit, the key circuit to explain this. And here it corresponds to a true experiment that has been done at Yale on this kind of circuit. So here you recognize the Transmont here. You recognize it. And in general, they couple it through small capacity to some pre-filtering, of course, which is called Purcell filter. And here you see the in wave, the output wave, okay? And here you see some amplification process, and all these things are very, very nice, have been very nicely developed by physicists. And here it is the stochastic master equation, which was used in this paper to, in fact, represent, when you measure typically one of the two quadrature of a cathode field as a homodine detection. Okay. And here it is just a 2x2 matrix because it is a two-level system. So I will not go into the details. Now let's go to what are the key characteristics of the stochastic master equation. So look, you start from this, and remember, I say, well, I have this equation which looks very different from this thing on one side. I have rho plus, it is something where I have an operator, rho, an operator here, and I normalized here. But you can write more or less your stochastic differential equation exactly the same way. So you have this equation with the Ito rules. With the Ito rules, by definition, what is rho at time t plus dt? It is rho plus. Okay, once you get a small information, which is dy. So, okay, for typical quantum circuit, the dt is, I will say, around 10 nanoseconds. Each 10 nanoseconds, you get a small information, okay, which is very noisy. Then what you have, you see, you can write down this. It is a very good exercise using Ito rules. It is exactly this formulation. So you see, you take rho, you sandwich it between m and m dag, you take the same rho, you sandwich it between L and L dag, and you normalize. So you see automatically that the trace of rho is 1. First thing. Second point, you see automatically that rho remains positive. Always. You cannot cross 0. It is not negative. Okay? And which means that this differential equation like this preserves the geometry of a quantum state space, which is the convex set of Hermitian operator, non-negative and of trace 1. So the way to prove it is like this. It's the simplest way. And here you go back more or less to the quantum postulate, okay, with this. So it's another way coding the progressive collapse of a wave packet due to the measurement here, and of course the M depends on you, your control. Okay. And from this, you see that you preserve positivity. It gives you some things to do numerical scheme, preserving positivity of rho directly. And also what you can prove is when something which is important is when the detection efficiency is 100%, since you know everything on your system. If your system initially is of rank 1, it remains of rank 1. Okay? The fact that, you see, with the Schrödinger equation, rho is of rank 1. It is a projector on the line. Why I need rho, okay, of rank 2, 3, 4, and so on? Because sometimes I have not the entire information on my system, and I have to do some mixing. You can mix density operator, you cannot mix unitary vector on the sphere. It's much more complex to do some averaging. Okay, just for this. Okay. Another characteristic, I will pass quite rapidly, is that this equation is an operator equation, which means it is independent of the orthogonal frame you choose to represent your system, which means that if you change your frame, you change the origin of angle in your system, you have exactly the same equation. As for initial navigation, it doesn't depend on the initial angle you choose for the laboratory frame. It is the same. Here you have exactly the same, but what you have to do is just, here you sandwich between the two. U is unitary, so it's inverse. Of course, it is Hermitian transpose. And in the new frame, you have to change the Hamiltonian by this because U is changing, you need to add this term, and the L becomes a new operator. So it's very important to use this rule, because now physicists have developed a lot of things to find the good frame. In particular, the frame where, for example, where H0 is diagonal is interesting. Something like this, okay? Second point is assume that in this equation, your detector is out of order, is destroyed. You have eta is equal to 0. When eta is equal to 0, you see that your detector measures only noise, not connected to the system. You have no measurement back action, and your system evolves according to a deterministic equation. This deterministic equation is called the Lindblad-Kozakowski equation. It is this one. And it is something which is a contraction. So Schrödinger evolution preserves a scalar product, so it's just a unitary evolution. But here you tend to contract the trajectory. And for a lot of distance, you have a nuclear distance, you have also the Hilbert metric on the cone of non-negative operator, but it is L1 construction. So it is not L2. Because rho is positive. So, and one point of this L1 property is that assume that you find an operator A satisfying this, I will say, matrix inequality. Okay? You assume that A is positive, non-negative. Then this guy, which is a linear function of rho, is a Lyapunov function. You have Lyapunov functions which are linear functions. As in the classical case, when you have positive system, okay, where live in the positive ortho, you can use linear function as Lyapunov function. But here it is an operator. So in the case of eta is not equal to 0, it is a super martingale. And you can use that to develop, of course. So you have a starting point of Lyapunov control design. You need some initial Lyapunov function to guess. Okay? This is a way to do control with this. Okay. So I think I will skip this part. I will go directly to the feedback scheme.
So measurement-based feedback. So it's something that you can imagine. You have a stochastic system, okay? It is a quantum or not. So you have a stochastic equation between relating u and y, and you close the loop with a classical controller. It's something which is known as the control of a stochastic system, and the fact that you don't measure rho directly, it is called a hidden state stochastic system, okay? And if you look in the literature in our community, it is something where you can do Lyapunov things and so on. Okay. So you can also do something which is very specific to, in fact, quantum system, is when you see my classical input u. It is a stochastic process, but a classical one. And if I assume that u dt is k dy, so it is just proportional feedback, in this case, it is called Markovian feedback. So this comes from, in fact, the seminal work of Howard Weissman in Sydney. Okay. This is called Markovian feedback, and in this case, you still have an ensemble dynamics, which is a Lindblad equation. So what is the ensemble dynamics? It is, if you look here, so here you take this and you take what is the expectation value of rho of t, knowing rho of t plus dt, knowing rho of t, and then you cancel this and you obtain a linear equation. So you have an ensemble average dynamics for rho, okay, when u is a known signal, okay, which is linear, which is quite nice, in fact. Okay, but you have this in this case, where as soon as the controller has some memory, you cannot use that. And now, the only things I know to prove stability in this case in the closed loop is the Lyapunov technique, because it is intrinsically nonlinear. Okay. Coherent feedback. Coherent feedback, it is the case where your controller is a coherent system. So in this case, you have to play with this rule. Your system, and you will attach to your system another one, and you have to design the interaction. Okay? And in this case, we go back to old things. It is the watt regulator. You have a steam machine, which is more or less an integrator, and you connect it through mechanical link, okay, to the two-ball system to regulate the velocity of a machine, the state of a machine. Here it is more or less the same. So you can imagine your system. You have to engineer to say, well, I will take another quantum system living in another Hilbert space. I will connect them with some quantum interaction, so it is an Hamiltonian. I know that this guy is not perfect. It has some decoherence, some damping. I know that this guy also has some damping, and I remain in the quantum world. So this idea of, I will say, dissipation engineering, which is well known in vibration control in structure. You use at specific points, you use some damping, or you change a little bit the mass, or you use some damping to avoid or to control the node of the vibration of your structure because they could be dangerous, okay? It's the same, but at the quantum level here. So the idea goes back to, in fact, optical pumping, where for which Alfred Kassler won the Nobel Prize I think a little bit 10 years later. Also known as population trapping, so it's purely physics. Then it is also known, so in Magenta you have a colleague from physics colleague, and in over it's much more community. And this is called dissipation engineering. They call also autonomous feedback, you see. And here you have a nice theory which has been, in fact, highly developed by our colleague John Goff and Matt James. Matt James is Matt James which is in Australia, you know, comes from H infinity. So a very nice theory of SLH theory, which is well adapted for quantum system, but it is in the dual formulation in Heisenberg picture. I will not speak here because it is difficult to engineer. it is I will say, with this SLH theory, you can interact, you can do interaction with your system in a much more flexible way. Here I use only a Hamiltonian interaction, but I cannot use a loop. First system, cascade in another system, and cascade in another system. If I want to do some cascade and then feedback, I will need this SLH theory. Okay? But just I will concentrate on this thing here. Okay. And of course, how to merge measurement-based feedback and classical feedback. Okay? So how time? So I have to finish at what time? I have 10 minutes, so I think I will. So here, let's detail a little bit coherent feedback. What you have is this. So you know HS, your data is HS, and the dissipation on S. So which is why I tensorize always with identity on the other space. I have exactly the same thing, but I have to choose my controller and its dissipation here. And I have to design this guy. And to design this guy, I have to take into account what kind of quantum system I have at my disposal, experimentally. Okay? And typically, in quantum circuit, it is damped harmonic oscillator, but the quantum one. So it is the simplest quantum system which has decoherence. It is a damped harmonic oscillator with a very high quality factor. Okay. And then you have different time scale. The time scale are as this one. So you have the Bohr frequency, okay, the frequency of your system and the frequency of your controller. Okay, quantum systems are oscillator. And the frequency is very high with respect to their, in fact, damping factor. So you have this, and with respect to the coupling. If you take two oscillators and you couple them in a very strong way, you obtain two other oscillators, but with a completely interaction between the two. So the coupling is weak in general, and the damping also is weak, so high quality oscillation. And the last point in general, what I have seen in experiment, is that the dissipation rate in your system, which is where you want to store the information, quantum information, so it's almost perfect system, is much smaller than the dissipation rate in the controller. Okay, you have to use this. Which means that behind this time scale, you have different perturbation techniques that will be very useful. First, when you have high-frequency oscillation, you need averaging. And up to now, people use what is called rotating wave approximation. It's first-order averaging. But since all the development that has been done for celestial mechanics, for example, you know that you can start the series, second-order correction, third-order correction, to increase the precision. And here, when you have some very different, in fact, here, it is a quality factor and damping rate. You can use also slow-fast system, singular perturbation, Tikhonov theorem, and so on. But you need higher order expansion, higher order terms. Tikhonov theorem, when you use the classical quasi-static techniques, is the first order terms. You need to use some invariant manifold theory and so on to do the asymptotic expansion. And it will be important to increase, in fact, the quality and the precision of a reduced model that you can use. Okay. So merging the two, well, it's quite simple. So you have your system here. You know that in general, you never control directly your system. You control this one, and then you control this one. Here, you never measure directly the system. You measure it through this one who has interacted with the system, and then you close the loop. So it's for obvious this. But in this separation, more or less, here you try to control the fastest decoherence, and here you try to finish the job, I will say. Because it is much more flexible to change a classical controller than to design a new quantum controller. Because it is, I will say here, more or less hardware, and here it is software. That's classical software here. Okay. And now, when you go to quantum error correction, so I will skip very rapidly quantum error correction from scratch, so you will see the slide. So, you know quantum error correction is just this. So classical things, you have a bit, logical bit, but you have to encode it in 3 bits. It's the simplest classical error correction technique. So you have 0, 0, you have 0, you encode it in 0, 0, 0. And you assume that you have 1 bit flip with probability p, okay, during the time delta t. And you want, in fact, you obtain after delta t, you have time, maybe the first one has flipped to B1, the second one to B2, the last one to B3. But when you take a majority vote here, you recover only one error. If you have 1 error, you can cancel. You can correct this error. If you have 2 errors, you are done. It's not possible. But in this case, this logical bit has a probability to flip with this scheme, feedback scheme, is less than p. So you decrease by this, by redundancy. You can do more or less the same thing for a quantum system, for a quantum qubit, okay, for a qubit. But in this case, for example, for the first idea of Peter Shor here, you have to encode your system on a tensor product. You see, you have the first qubit, C2, the second one C2, the last one C2, composite system. And the logical qubit will be the physical 0, 0, 0. So you are still in C8. Cool. Okay, if you want to control over, because you may have not only bit flip, it is only what you can have for a classical bit. You have also phase flip, because the relative phase between 0 and 1 in this thing can change. In this case, you can imagine something the same. You can do exactly with bit flip and phase flip, which gives you any error on the qubit. So I will not enter the detail, but after that you will see you have to increase the dimension of the state space, of the Hilbert space. So at the end, if you look at, I have a resource, a certain number of physical qubits, okay, and I want to encode with the physical qubit a logical qubit. And I want, with this logical qubit, I want to correct only one of the error on a physical qubit. What is the minimum dimension of a Hilbert space to do that? The minimum dimension is 32. C32 is quite a large Hilbert space. And now, if you imagine, in fact, more complex, for having a first order correction, if you want to go to a second order correction, in fact, to detect with your scheme during a sampling period 2 errors. You have to increase and so on. And after that, in the estimation of Martinez, with typical qubits like this, you have to use 1,000 qubits, which means that you are in the Hilbert space C2 power 1,000. It is infinite dimensional Hilbert space. And even this guy is infinite. It's quite large. When you take 32 modes to represent a differential equation, it's quite a very good approximation. So the idea, in fact, of Maziar and Zaki with Michel Devoré at Yale is directly to encode your physical qubit, your logical qubit, in the infinite dimensional Hilbert space, which is you encode your system in a harmonic oscillator. A harmonic oscillator, you have here the vacuum, the first photon state, and so on. So you have the Hilbert space, labeled by n. And here it is typically exactly the quantum analog of a damped harmonic oscillator. It has a completely counterpart at the quantum level. So the pulsation of the oscillator is omega. And in fact, the dissipation rate is kappa s. And in general, for quantum circuit, you will store your qubit in this very high quality oscillator. You need 10⁶ oscillation to see that on the amplitude, things go down. So which means that you have to go to the rotating wave frame, which means that you eliminate this guy, which is much larger than this one, and you obtain only this one, which is with another frame, in fact, the analog of the amplitude equation. And for this system, which is quite nice, is that you have precise state, which is more or less exactly the same as the amplitude of a field, which is our coherent state, which are quite robust to, in fact, the finite photon lifetime corresponding to 1 over kappa s here. This is coherent state. And these coherent states are very easy to prepare. And what you want to do is to store quantum information in coherent superposition of these two coherent states, which are called, in fact, in the quantum literature, Schrödinger phase cat, because you defined the module of amplitude, and you want to code your system in this thing here. So you have a module of amplitude alpha. It is where you want to store your system. You have E alpha here. You have minus alpha and minus E alpha. Okay? If I was for a classical system, I will have here a Dirac here, a Dirac here, a Dirac here, and a Dirac here. Okay? And I will switch between, I will jump between I am in this state or in this state or in this state or in this state. Now, if you represent this kind of Schrödinger cats, the way they represent this, it is which is called the Wigner function. It is a sort of quasi-probability law in the phase space. And you see that the fact that it is a superposition, coherent superposition, because you have blue things in the Wigner function corresponding, in fact, to negative part, which gives you that is a true quantum state. Okay, so and one of the possibilities to engineer an environment with feedback for this system, it is inspired by a recent experiment in Yale and an experiment which has been recently done in our group in Paris, especially by Zaki Lektas, on a first experiment to try to, in fact, to suppress, for a quantum bit, you have two kinds of error, either bit flip or either phase flip. With this structure, what you get only one bit flip. You automatically suppress phase flip, which is quite nice. And they show the first experimental proof that with this kind of stuff, so with this sort of quantum controller, you can extend the lifetime of your system. And here you see, so this is the storage where you want to store your quantum information. And to engineer something around this, you use another oscillator, another one here, and you try to engineer such kind of coupling, the A or the annihilation operator, where here you use this cavity here, and to see the scattered light, the scattered wave scattered by the cavity here, gives you some information on, in fact, on the parity of a cat, and here gives you the pumping to remain, in fact, the cat at a specific alpha. I will not enter into more data. But in this scheme, you have many time scales. And you can use perturbation theory averaging to decrease this, to achieve a reduced order stochastic master equation on a 4-dimensional space. And now I finish. So I guess that quantum engineering can be very useful for robust information processing like this, to give some new idea. Just by maybe a first structure, reasonable structure, will be to have this 2-time scale, fast time scale here, slower one, slower here, in a certain sense. And the last point to conclude is that there is a need to develop some mathematical methods adapted to the structure of a system, okay? The first mathematical method to the stochastic master equation is to use averaging of the stochastic master equation and singular perturbation techniques, high order one. And for this part, it will be, I think, useful to develop adapted stochastic technique with Lyapunov function, control Lyapunov function. So thank you.